Hey everyone, welcome back to the channel. First off, I just want to say a massive thank you for all the love and support I received on my first video, I think which was released way back in the month of December. Honestly, I didn't expect people would be, watching that video and, posting comments on that. I'm so grateful for each and every one of you who took the time to watch, comment, as well as subscribe to my channel. It means the world to me, and it's really motivating me to keep going. Your amazing feedback has given me the energy to keep creating content that dives even deeper into what I'm truly passionate about, teaching robotics, which is free of cost. As in the first video, I already explained regarding how to integrate any kind of CAD model into your the ROS2 environment, which was a mobile robot, right? Differential drive robot. If you have not seen those videos, if you've not seen that video, I put only one video to be honest. You could go back to my channel and watch that video. But from now on, I would be making the videos on the topic that is, as you can see in my screen, that is integrating simulation and hardware for a custom robotic arm with the ROS2 and MoveIt2 API. So what does this mean? That means I would be, teaching you guys as in how to build your own custom robot, or if you already have one a custom robotic arm, then how do you, put how do you convert that the CAD model into the ROS2 environment? And with the help of Movie2 API, we can we can integrate the motion planning control ROS to control and some of the real world examples of how ROS 2 can be a game changer in robotics. I would be going through that. So if you are excited about learning more or have a specific questions or topics you would like me to cover, make sure to drop a comment below, and I'm here to help, and I want this channel to grow with you guys as a community where we can all share and learn and share knowledge. So yeah, so before I progress with this first video of how to convert your robotic arm into the ROS2 file or a ROS2 environment and use it in a ROS2 environment with the MoveIt2 API, I would like to take some moment and ask you a question. Why choose ROS2 for controlling a robotic arm? Why ROS2? I mean, I know it's a powerful framework for designing and developing of advanced robotic applications, but why ROS2? Why not the ROS, or why not custom integrated softwares or the custom integrated the algorithm? It all works well. Everything is fine until and unless you are comfortable with integrating those techniques into your project. But the problem with all this is the cross compatibility. There is an issue with cross compatibility, as in, let's say that you have built a robotic arm and you have coded, you have done some changes, you have done some code in your project file, and if you want to transfer the project to somebody else, and he has to go through this from the scratch. But if you have a roster framework, everything is maintained. Only has to know the hardware drivers instead of knowing the stuffs which he wants to control or something like that. So ROS2 framework will make sure that we are all on same playground, and we have to just learn how each drivers or each motors would be communicating, that is hardware drivers, how those hardware drivers will be communicating with our ROS2 environment. But once you guys know what is ROS2 environment, you don't have to learn from the scratch. So that is one of the advantages. Okay, now let's see the result of the end result of what you gonna achieve by going through this playlist that I'm going to create from today onwards. One is simulation, as in you could see a robotic arm that is deployed in a simulation environment called as Gazebo, and you could control it in a move it to API. The control of a robotic arm is with the help of ROS2 as well as with the help of MoveIt2, we could achieve that, the same robot that you're going to deploy in the real world can be visualized even in the simulation environment. So as you can see, I changed few parameters here and there, and I try to change few of the joint angles and it moves respectively. And apart from that, you could see some of the visualization. I mean, you can integrate the simulation to the real world robot. As in, whatever you see in a simulation, you could implement in a real world robot. That is something possible too. This video is quite not that good, as in I've just it is just a prototype, and once I tell you how to do this kind of simulation with the hardware integration, it becomes way more evident. As in you could also deploy your own custom robotic arm, and you could build your own one, and you could simulate using the ROS2 environment. That's the whole idea about how this works. See, you could see the gripper that is getting moved, and in this video, you would be able to see the movement of the whole joint angles to be precise. So you see, these things are possible uh, by going through this playlist. And if you got any doubts, please put it in a comment section, and I would go through each of the comments, and I would uh, try to find some solutions to your doubts. And I would like a feedback too, as in a feedback as in what I could improve. I know I just blabber a lot, but it would be very way more easier if you guys comment to these videos, as in what changes needs to be done in the upcoming videos. And yep, let's get started. So as you can see, I'm in SolidWorks, the environment. So if you see the heart of today's topic, that is converting a robotic arm design in a CAD software, and here the CAD is a SolidWorks software into URDF model. The process actually begins with creating a detailed 3D model of the robotic arm in the CAD, which I think if you go through, there are a lot of playlist on the YouTube, in the YouTube, as in how to create a CAD models, as in how to create a CAD models from the scratch. If you're a beginner, I would suggest few playlist that I would put it in my description. You could go through my description, and you could go there, and you could see as in how you could build something from this scratch, CAD model, using CAD model, that is specifically here SolidWorks. And one thing is that I could have gone for any other softwares. It doesn't have to be a SolidWorks, but I've chosen SolidWorks for several reasons. One, it is easy to use, and I'm more comfortable with SolidWorks, as I've been using this from my engineering. When I got into engineering, I've been using this SolidWorks, and it's been carried till now. And apart from that, you could even go for NX, Siemens NX CAD software, which is also quite famous. But another advantage of going for SolidWorks is that there is a plugin, which I will be going through the later part. There is a plugin called as Export as URDF. So this thing is quite helpful for me. I mean, this plugin is not available with any other CAD software that's available in the market. This only supports the SolidWorks. So this kind of a plugin is way helpful for me to build something which might be as simple as this, or which might be a complex CAD model into the URDF, that is Unified Robotics Description Format. This Unified Robotic Description Format would be used in the ROS2 environment. So the process begins with the creating a detailed 3D model of the robotic arm in CAD, which is this. And once the model is complete, we convert it into URDF file. And the URDF file would look something like, if you go here, this is how the URDF file would look like. So just once. Yep, this is how the URDF file would look like. So the URDF file has a lot of information. As in this information here, the holds regarding regarding what is the origin of what is the origin of the links, and what is the origin of what are the values, and how, see, the CAD model depicts in a visualization form, but once you put it in a URDF form has a certain format which will make sure that these visualized formats are put it here, as in what is the angle it has been rotated, what is the angle at which the first link is located to the zeroth link, or second link is located to the first link, what is those values, and what is the inertia parameters, and what is the name of those links, and what is the origin, and if you see the link 1, which is quite different from the base link, and if you see the link 1 here, this link 1, how it is related to the base link. So how all these informations which are quite visually appealing in the SolidWorks, as in which is available, which you could visualize it in SolidWorks, can be hard coded in this fashion too, in this format too, and this format we call it as URDF. Okay, so something this is very important, and this thing how this is important you will get to know in the upcoming the sections that I'm going to uh, put it in the YouTube channel, and we could go through that. But before that, we have to come till here, as in we have to at least convert our CAD format into the URDF format, right? So that is something which important, and this allows the ROS2 to understand the physical properties of a robotic arm. Like I said, once we convert it into the URDF, this helps the ROS2 to understand the physical properties of the robotic arm, including its dimension, the joints, as well as the links. What is the link, where it is located, and how it is located? What is the color of the link? What is the material? What is the geometry? And where this link is located in your system? Everything you would get the information once you know how it is being converted. So let me just stop my talking and show you how show the how do we convert the process. So first of all, we have to go to Google, and of course everybody knows this as in going to Google and typing out. I think if you have seen my the previous video, even I have suggested that you go here and search for this SolidWorks to URDF converter, and over here you've got something. If you go to this website ROS Wiki, over there you have an installer. You download this installer. Once you download, it's quite easy. You would understand if you go through this tutorials or something like that. It's you don't have to go through any tutorial. You just download the installer. It would automatically once you run those installer. I think it's named as SolidWorks SolidWorks 2. Let me show you guys. I mean, let me just download this installer. Yeah, it comes in this zip file, or you could download it with the .exe. If I go here, sw2 exd ex xw sw2 urdf setup. I think I have deleted that, but anyway, you could always download this .exe file, and we could go here and you could run this. Yes. See, it is a quite explanatory. You install this and automatically what happens? I have already installed this, so I don't want to install it once again. So what I'm going to do is I will show you after installing where this plugin comes. If you go to the tools, initially you wouldn't be able to see the plugin down, but you have to come down, you have to scroll down. Once you scroll down, you would get something called as export as URDF. So once we click on this, we can convert any CAD model to the URDF format, which is quite simple as it sounds, but it is not. If you directly do that, it causes an error because you have to set the angles, it's not angles, sorry, my bad. You have to set what is the axis, what is the coordinate system or coordinate frame. So in order to understand you guys, as in what I'm saying here, it's better I would show you step by step as in what I'm going to do right now. So go to the insert tab here. There is something called as reference geometry. So in the reference geometry, there is something called as point. So click on this point and click here. So you get this nice little preview here, which says the point is going to come here and click OK. So you have already created something called as point 3. By default, it should come as point 1. I don't know why it is showing as point 0.3. You could always rename this tree item and you could name it as point 0.1. Okay, now once we created this point 0.1, we have to create similarly for every other joints. See, if you look at this robotic arm, we could see that this is a base link. This is one more link. This is one more link. See, as you can see, it rotates here, and this is one more link which moves up and down too. I don't know, for some reason it's not moving. It's not trying to move, but it has to move. And if you see here, this is also one more link. And if you see here, this is also one more link. This is also a one more link. And here you have got a gripper, right? So here you have got a gripper. Gripper in the sense which rotates here, as in we have a joint here, a revolute joint, that in turn rotates this link and in turn makes this whole thing to rotate in a place. I think you're getting my point. I mean, what I'm trying to say that this gripper has only one the revolute joint and the rest of them are meshed together, so it rotates accordingly to the dimensions, or according to this the robotic arm. I mean, that has been built, right? So yeah, so there are how many degrees of freedom? You know, if you don't consider this gripper part, there are one, two, three, four. 4 and 5. So this is 5 DOF, or 5 degree of freedom robotic arm. So each joint must have its own the point like I've defined here, and it should have its own the axis about which it rotates. So if we see why we have to do this, if you are asking me this question, why we have to do this, if you directly go and export as URDF, now, there is a high chance that it would automatically take a wrong axis and the point about which the axis will be generated and about which the joint will be rotating about that axis, which is not suitable in our case. So what we do is that we already define what axis and what point it has to take, and accordingly it has to generate a URDF model, right? So yeah, let's just quickly create the point. Let's go here and let's insert one more point. So insert, as I said, go to reference geometry. There is a point for this link. Where this point should come for this link? It has to come here, right? In between here. So yeah, that makes point 2. Now insert reference geometry point 3. Point 3, I would like to come. I would like to make this point to come here because this is the axis of the rotation. And see, if you don't cancel this point 2, it would automatically take this as also point 2. So delete this. We want only the point to be coming here in this edge. So click OK. I hope it's it's clear. It's not that confusing. I believe we are just creating a point for each joint or each revolute joint. Okay. So reference geometry, there's a point. This we'll delete this, and yeah, press escape so that it's not that confusing. Press escape. Now we have one more joint here. Let's go here, insert this reference point. This is the point. Click OK. We got point 0.5. So how many points? We got point 0.1, point 0.2, point 0.3, point 0.4, point 0.5, and we need two more. That is point 0.6 and point 0.7, right? So insert. We'll go here, the reference geometry point. Mm, delete, click right, click OK, and we have got here one more point. Oh shit, what happened here? This is not preferable. Yeah, this is fine. Point 0.7, point 0.7. Now press escape, go to insert, reference geometry point here. Okay, click OK. Then here, press escape, insert. This is a little tedious job, but I would tell you that this is okay compared to creating a URDF from the scratch for this robot. Usually, so we have to create URDF uh, from scratch, as in we have to set few physical parameters such as the joint angles, dimensions, and links. But going through these steps will automatically select what needs to be done by the library that we have just inserted here, right, into this software. So we click here and click OK. Then we press Escape, go to Insert, Reference Geometry, Point, make one here, select yes, press Escape, Insert. We got we got a reference geometry point here, press Escape, Insert, Geometry point, click, OK, press Escape, Insert, reference geometry point, press Escape, Insert, reference geometry point, press Escape. So yeah, we have successfully created mm, yeah, points to the each individual axis, right? So each individual joints. Now the second, I mean, two more steps are there before we use that plugin. The one other step is creating an axis, individual axis. And how do we create that? We go here into the Insert tab, you go to the reference geometry, we select the axis for the base link. This is the this is the axis. Now click on the cylinder and it automatically detects what axis. You could see the small nice preview of where the axis would come. You could select that and click yes. Okay, now press escape. Now insert. Now once again reference geometry axis. This is how, this is for link 2, and you could see the for link 2 this is the axis. I mean, you don't have to create an axis for this link 2. You could always choose this axis 1, you know same as same for link 2, because they are coinciding with each other. But anyhow, I would just create one more just in case you don't get confused later part. Then yeah, the once again we go here, we press escape, then we go here reference geometry axis, then we click on this and you could see the small nice preview of the axis. Click on yes, this is where the axis should come, that is where the axis of rotation would be coming there, and press escape, then go to insert once again axis. See, to make it not so confusing, I could always copy the previous axis and I could paste it there and I could rename it. We could that is up to you how you want to minimize the time, as in how do you want to optimize this process. But I'm here detailing this process so that you could see what is going on, okay, step by step. So this is the cylinder. We'll create this. It's nice preview, good. Then click es then press escape, then come here, click on insert, and reference geometry axis. We click here to this part, and this is the axis, and click on yes, that's the axis. Oh, let me just see where this axis has been created. Yeah, it's good, it's parallel. And second, I would like the one more axis to come here. Okay, it's not reading. Yeah, this is good. Now this is the axis. Press escape. And now I know this is a very tedious job, as in we have to select axis for each and every joint. But anyway, this is fine compared to creating URDF from scratch. Sorry, yeah, my bad. What happened? Yep. Insert, we would go here once again, reference geometry. Then we have got axis. Then I hope this is understanding, as in this is not that confusing as it sounds, I believe. I mean, there's nothing. I just inserting few axes here and there, and wherever you find joints in your the robotic arm, just put axis there. Okay, it might be a revolute joint or prismatic or anything. It's fine. It's up to you. That we would define it whether these joints are revolute or whether these joints are prismatic. We would define it in the SolidWorks to URDF converter. But before that, we have to create all these steps. Okay, so I'm repeating that same thing whatever I've repeated that time, but that's important to understand. Okay, insert reference geometry. Here we have got one. Click yes and click escape. Insert reference geometry axis. Here one axis. Insert reference geometry axis. Okay, yeah. The last step before we use SolidWorks to URDF converter plugin is going for coordinate system, which is way important. Okay, very, very important. See, it automatically took this point, but you could select any other point that I will show you later. But anyway, it has selected the point. Now, the main idea or the main goal here is to define the z-axis. If you see here, small preview of which color represents which axis. Let's say the blue color represents z-axis, green is a y-axis, and the red one is x-axis, right? So the small preview helps you to identify which axis we are dealing with right now. See, it automatically took z-axis along this axis or along the revolution of that link or the joint, right? That's what we want. We want z-axis to be pointing in the direction uh, where our robot joint is going to rotate. As in, we want it to point it in a direction about an axis. Okay, so the z-axis has to be pointing. Keep in mind that z-axis has to always point about about the axis, axis that we have defined. That is axis one. See, this is the line of the axis. That's where it has to define. Or in simple terms, it has to be facing or it has to be pointing towards the angle of rotation where it is going to rotate, right? So this is about this axis. This link is going to rotate. Even though we making it stable, making it sit down in a place and we are clamping it in one place, but given a chance it would rotate about this axis, right, about this joint, right? So hence we define this z-axis about that axis. Okay, I hope this is clear, and it would be clearer when once we define it for each other links. So anyhow, I like this part. Okay, so the z-axis is pointing there, and it's good. Let's click OK. So you see the coordinate system one. It automatically defines. Let's say that you are not able to visualize all this, the axis or the coordinate system. What you have to go do is that we have to go to the view bar, and there is something called as hide and show. You go on and select axis and coordinate system, and if you want the center of mass, you could even select the center of mass. But anyhow, we are interested in axis and coordinate system. Let's say that you unplug, uncheck this bar, and it automatically disappears. So that's the default case. I think you guys will be not able to visualize this, but if you want to visualize this, you have to select this. You have to uh, pin this, or you have to click this coordinate system here, okay, and as well as axis. So how I hope this is clear. Now coming to for this link we have to select the coordinate system. Once again we go to the insert tab. There is a reference geometry and there is something called as coordinate system, and we would go and select this part, which is point 2, I believe. Yeah, point 2. And where is this the axis of rotation? This axis of rotation is same as the axis of rotation of the base link. You could change the direction. You could always change the direction. That's up to you. But I would keep the direction upwards. That's the pointing upwards, z-axis, and I want x-axis to be pointing in this direction. I want x-axis to be pointing in this direction. So we always keep this general rule, As in, I have made a mistake even in the previous link. I will come to that. But here, I will make it clear to you guys. As in, once we are defining coordinate axis, the coordinate axis, the z-axis has should always be pointing towards the axis of rotation, and the x-axis to be pointing towards the length, the link length, or whichever the direction your robotic arm is facing towards. Over there, it has to be pointing. Okay, so y-axis, we don't care because it automatically aligns once we align the z and x-axis. I hope this is clear. And coming back to this, the coordinate frame 2, if we, oh, what happened? Where is this coordinate system 1? Coordinate system 1. So once we try to edit this feature, okay, I would delete this coordinate system 1 for a moment, and reassign this value, align reference geometry coordinate system. Okay, this is good. Z-axis is pointing there, but I want x-axis once again. I would repeat, z-axis to be pointing towards the axis of rotation, whereas the x-axis should be pointing towards the direction in which the robotic arm is facing. Okay, in this direction, in my case, the robotic arm is facing here. In your case, the robotic arm might be facing a little opposite, depending upon your the design. It doesn't matter, but choose one configuration and you follow that configuration throughout the geometry, throughout the assignment of the coordinate system. Okay, that's important. I hope this is clear now. Now it is making it as coordinate system 3. Let's rename this as, I don't want this is actually 1. Now, yeah, let's go here and once again we insert something called as a coordinate system onto this point. Yep, and the z-axis should be pointing to this, and the x-axis should be pointing to this, and we are good now. Okay, coordinate system 1, coordinate system 2, coordinate system 3. And once again, for this, we would go here, insert tab, we would go reference geometry, coordinate system. We have got point 4. Sometimes it doesn't recognize. If you don't recognize, you could always come here to this small section bar that you see here. Just uh, open this tree and come here, and we know that this is point 4. Select point 4. Okay, you could always do like this. You could try to select the points from here, or if you're not able to see, or if you're not able to click on the points, then you could always open this tab and you could select the points that you're interested from here in this tab. I think it's clear. So z-axis to be in this axis, and x-axis is pointing towards here, which is good. But anyway, I would make sure that it is pointing there. Yep, good. Then we would yeah, we would go here to this joint angle, then insert reference geometry coordinate system to the point 5, point 5, and the z-axis should be pointing towards the axis 8, z-axis axis 8, and x-axis, what I could do is that instead of pointing there towards outside of my plane, I would like to keep everything in a single frame. Mm, yeah, the x-axis is the red one. I would like to keep it upwards. Upwards, yeah, this is good. Now the z-axis. See, if you are in a dilemma, or if you get into a position where you are not able to assign x-axis because the z-axis is aligned towards the x-axis of the previous one. let's say for this coordinate system, if you see here, the x-axis is pointing like this in this direction, but here with the z-axis is pointing here. Then if you're questioning now where I have to align this x-axis, the general rule is that you keep everything in a single plane. Okay, if you consider this as a single plane, then the x-axis you could keep it upwards or downwards. That's up to you. But I would like to keep it upwards. But what if you are keeping it the x-axis in this direction, as in the direction of y-axis? As you can see, the y-axis, instead of y-axis, if you would have kept the x-axis in this direction, that means the x-axis is projecting out of the plane. That's something that I don't recommend usually, because the plugin doesn't understand all the time that this is what is happening. So the general and the best rule is that you keep everything in a single plane. Okay, for me, this square box is a single plane that you and me are visualizing right now is a square, or rectangle, or any plane, any shape form of plane which is directing towards our towards our view and viewpoint, and that's the plane that we are interested in. And in that plane, I would like to keep the z as well as x-axis. So keeping that in mind, these general rules, I think most of you got those doubts that could be cleared. Now, coming here, let's just fast forward this procedures a little faster. I mean, not making this more boring. Z-axis should be pointing this axis, and x-axis I want it to point it in this direction so that it becomes clear. Oh, is it a little? Wait, x-axis, right? Now let's delete this, and I want x-axis to be pointing like this. Okay, now it makes sense. Okay, now we click on clear. Okay, now we have x-axis, z-axis here. Now, yeah, coming down to insert reference geometry, we have got we want z-axis to be pointing like this. Oh my God. Let's say that it's upwards, and we want x-axis to be pointing in this direction. And I hope it has done the changes necessarily. We click on OK, and oh, it has yep, it has done the changes. Okay, it's good. I thought no, it's why it is tilted a little. Clear selection, Z axis. I think it is good. Now going to insert reference geometry. Point 8, point 8, point 8, yeah, point 8, and z-axis to be want it to be in the axis 11, going upwards. Sorry, instead of clicking upwards, I just clicked down, and I want z-axis to be pointing in the same plane. Insert tool, reference geometry, geometry, point 14. Okay, this is good. And insert options, reference geometry, there is a coordinate system. We go for axis 12. Not the axis, sorry, the point 19. We do have point 19, right? Okay, why it is not showing here? Oh, this point 9, my bad. Point 9, and z-axis is axis 12, axis 12 showing upwards, and x-axis is pointing in this direction. Now go here, insert tab, once again reference geometry, click on the coordinate frame, and I want the coordinate frames to be generated 1, 2, 3, 4 places at the 4 places. Now we have axis, we are interested in point 11. Go here, point 11, and I want z-axis to be pointing towards axis 17 in the upwards direction, and the x-axis I want you to point it. Oh, my bad. What happened? Yeah, towards this plane. Click on yes. We are good to go. Click on escape. We've done one. Three more to go. Bear with me, guys. I mean, it's it's kind of tiresome. Even I'm feeling bored. But anyway, we have to do this before we use those plugins. So yeah, 15 axis 15 x axis. Insert reference geometry coordinate system. We'll go for point 12. Point 12, and the z-axis should be pointing towards this, and x-axis should be pointing. Insert reference geometry coordinate system. Point 13, axis 16. Oh, yeah, now we have successfully, oh, it's too much clustered over there. But anyway, we have successfully created three pre-processing kind of techniques, as in what we have created points, we have created axis, we have created coordinate systems. Now, final and interesting part is going for this plugin, which is under tools section, and once again you will not be able to find initially where is this plugin. You have to scroll down a little, then you get this export as URDF. Once we get this export as URDF, which I have already created way back, uh, so it's kind of replicating the same thing here. If you see the tree structure, it's kind of replicating that. But anyhow, I would delete the one that I've created earlier, as in we can go and delete this section. Yep, we have to delete this. Then we get tool section, export as URDF. Now it starts from completely new, and you could keep the name of the link as a base link. Now it would ask the pre-processing steps that we have done is helpful here now. See, if you keep it as automatically generated, that's the coordinate system, it would come proper. It wouldn't come proper too. I mean, it would come right or wrong. It depends. Okay, it depends upon your robot, how complex your robot design is. If it is very complex, it would be assuming its own the axis about which trying to rotate or something like that. So if you don't want all those, you go here and select something called as your own custom coordinate system, that is custom coordinate system 1. Click on here, and this field here is telling you, see, if you just hover on this slight uh, the no help bar comes, that tells that select the components associated with this link. For the base link, what is the component associated? This is the link, right? This is the total link. So click on that, and what is the number of links attached to this base link? We have got one more link called as a link one. We could keep it any other link. See, compared to if you've seen the earlier video that I've put it in my YouTube channel, the first video that I've put it in my YouTube channel, over there was no doubt. as in there were no child link as such. There are only parent links. Okay, if you have any doubts, you could go back and you could check there. Even there I have shown how to convert any mobile robots into URDF format, but that is not the scope here. Here it's asking me, this field is asking me what is the number of child links associated with this base link. This base link has one child link called as waste 1. I have kept this name as waste 1. If you go here and if you check waste 1, this is the waste 1 here. So we have got one child link on. So let's click on this one and now click this empty link, which say if you downgrade this, if you make it 0, it just shows the base link. Hmm? It just shows the base link. But if you have any child link, then click on this, the empty link. Now you select the name of the link. Let's say that we would keep it simple as link underscore 01, and the joint name is link 01. Okay, you could keep the same name as a base link, which I would not suggest every time, but keep a little variation is suitable here. I mean, you see the base link has a link underscore 01 and joint name as a link 01, right? And if you see here the reference geometry, once again, it automatically generates. Since my model is kind of not that complex, so it might get right, initially. But if your robot is way more complex, it may not get the coordinate system as per your need. It would generate its own coordinate system as per its understanding, which is not suitable for your end use, right? So better, that's the reason why we have done all those pre-processing steps. So go here and select coordinate system 2, coordinate system 2, and the reference axis is axis 2. If I believe there is something called as axis 2. Okay, there is okay, why it's not showing? Let me check. What are the axes we have? Axis 1, axis 5. Okay, axis 5 starts from axis 4. Okay, that's the reason why I'm getting confused. Okay, axis 5, and joint type, it is a revolute joint, and the link is this link. And this has got one more child link called as this link. So we'll go here and select one and select this empty link and name this as link underscore 02, and this name as link 02. And the coordinate system is coordinate system 3, and the reference axis is 4 5 6. I believe that is what it is, 6. Yeah, 6. And joint type is, once again, we have got different joint types. We have got continuous, revolute, and prismatic. Since this is a robotic arm, we have a certain limits of angles, so hence it is not a continuous, rather it is a revolute joint. Okay, revolute joint, it doesn't continue 360 degrees. It's 0 to 360 degree. It has got some limit, 0 to 180 or 0 to 190 or 200, depending upon your the motors that you select. But here it is 0 to 180 degree, hence I'm going to select revolute joint. I think it's quite understandable. I don't need to go and repeat all this. Then this is the link we're interested, and this link has got one more child link called as this link. So we select one, go here, rename this link as link. We have already done link 2, so link 03. Name this joint type as link 03, and the reference coordinate system is coordinate system 4, and the reference axis is axis 7, and joint type is once again revolute, and the link that we are interested is this link. And this has got one more child link called as known as this one here, right? This one here, and the link is link underscore 04. Joint type, joint name is link 4. Reference, the coordinate system is coordinate system 5, and the reference axis is axis 8. Joint type is revolute, and we got one more, link underscore 05. Joint name is link 05, and the coordinate system is this one here, 6, and the reference, the axis is axis 9, and revolute, and this thing is this one, and this has got two child links. Okay, this link has got actually four child links, one, two, three, four, because these four, let's see that this gear is attached to this link, this gear is also attached to this link, this gear is also attached, this, the link, we say this as accessory link is attached to this link, the parent link, this is also attached. So there are four ones, four child. So one, two, three, four, four child. First child we would name it as gear gear 01, and the name here it as gear 01, 2, and the axis type is coordinate system is coordinate system 7, and the axis reference axis is axis 10, and the revolute joint is, I mean the type of joint is revolute, and the gear is this gear, and this has got one child link. So we'll go here and select this, and this is called as gripper 1 and gripper 01. I hope it is understandable. And here, if you go here and see which is the reference axis, that is coordinate system 9, and the reference to the axis, I mean coordinate system 9 is a coordinate reference coordinate system, and the reference axis is axis 13, and this is the child link, and this has got no more child link. So we end there and we go for, see if you see this bar, this simple tree diagram, preview tree diagram, you could see it defines, it asks, there are four more links that are associated with the link 5. This is a link 5, as you can see, link 5. Now we can go for the next link, name this link as gear, gear underscore 02, and this is gar 02. Automatically create, we don't want it to create automatically, we have to create it as a coordinate system 8, and the reference axis is axis 11, and the joint type is the revolute, and this is the one. This has got one child link, name it as the gripper 2, gripper underscore 02, and here we have a gripper 02, and the axis that the coordinate system that we are interested is in coordinate system 10, and the reference axis is axis 12, and the revolute is, joint is revolute, and this is the one. And if you go for another the link, now let's link it as accessory. I might do a lot of spelling mistakes here, but please don't mind me doing that. So accessory 01, and we have got accessory. Always try to keep your names in a small letter, not caps. A lowercase is way better here, and because it somewhat throws an error once you convert to URDF. URDF doesn't always assist you with the names that has caps in it. Okay, so yeah, coordinate system. We are interested with this coordinate that is mm, yeah, this is the coordinate system that we are interested is coordinate system 12, and the reference axis is axis 15. Automatically detect, this is revolute, this is the link. Okay, this, since this link is sharing the child, same child as this link, so what we could do is that mm, what we can do, yeah, this is quite challenging here. I mean, should we have to, yeah, we could do one thing here, that since this is sharing the same child as this link, you don't have to include this child link once again. Okay, you could end your link, the last link there. So let's see, accessory underscore 02. The name of the joint is accessory 02, and the coordinate system is coordinate system 13, and the reference axis is reference axis 14, right? It's Revolut, and this is the one, and that's it. We have completely see, since this the link is also sharing the same child link as this gear one, so we don't have to include this child link. Okay, we don't have to include this child link. So what we can do is that instead of clicking this green button, okay, we can go for something called as preview and export. See, it would take some time, and it would open this configuration tab, and you could check whether all the configurations are proper. So okay, so let's say that link one, right? Link one, there is something called as base link. Base link is always fixed, so we start from link one. Check whether the joint type is Revolut. Yep, it is Revolut. And do you need any effort to be in order to make sure that these things move? You could always add the effort and velocity. That's up to you. That's your thing, and you could add even dynamics as well as the damping. You could do that. We could go for link 2 Revolut, and everything is proper. Link 3, it is also proper. Link 4 is also Revolut. Link 5 is also Revolut. Gear 1 is Revolut. Gripper 1 is it's telling me it's fixed. Hmm. Let it be fixed for now. Let's see what output it gives when we convert it to URDF. Actually, it has to be a Revolut, I believe, but let it be a fix. Let's see what happens. And Gear 2 uh, is Revolut. Since Gear 2 is mimicking Gear 1, right? Once we already know that only one motor is attached here. Since only one motor is attached, that's the reason why the gate 2 will be mimicking the gate 2. All these assemblies will be mimicking this part, right? So let's see. Let's put this mimic joint, and let's keep joint to mimic is the gear 1. Gear 1, it has to multiply it by 1 and offset of 0.0. It has to mimic that thing. Uh, Okay, let's see. Gripper 2. Gripper 2 is also, it's taken it as a Revolut. Let's keep it as fixed for now. And yeah, this even mimics, I believe this also mimics the Gear 1. But okay, let's see. Accessory 1, accessory 1 also. This is the accessory 1, I believe that. Hmm. Hmm. Okay, let's keep this as accessory 1 as Revolut, and Gripper 2 is fixed, accessory 2 is also Revolut. And let's see, let's go here and press next button. Hmm. Let's see that where we could I put it in my. Okay, it has successfully exported our CAD model to URDF. But before we visualize this URDF in the ROS2 environment, it's always suggested that we, check it in the one more software called as URDF Web Weaver, because if any mistakes that we have done in the URDF, you don't have to check the errors by going to the Ubuntu environment and checking there in the Gazebo and coming back and revisiting this SolidWorks URDF plugin and making those changes. You don't have to do that. Instead, you could always go for something called as URDF Web Weaver. If you search it in a Google, and you would get this Web Weaver software, and you could go here. Something this was done by great huge thanks to Garrett Johnson, who has done a wonderful job in doing this web-based URDF viewer, which is quite easy for us to visualize our generated URDF model here. So let's say that we have already created a URDF model, and this is our URDF model. Yeah, before we, generate this URDF, I forgot to tell you one thing. Since I will delete this, I will go back to once again to this file, and I would go here and configure feature, not configure, suppress rollback. No, we go for here, preview and export, and we have created here. Everything is proper, I believe, fixed. Gate to gripper 2 is fixed, and yeah. So what I was trying to say is that once before you uh, install or before you put it in any of the folder, before you send this CAD model into the ODF for the model, you have to remove that the SolidWorks extension, that is dot solid assembly extension, and you have to save that. Okay, otherwise it throws an error. It's always suggested to do that. Once again, we go back here and we go to the download section and we put our model here. And as you can see, our model has been successfully been deployed as a URDF. I don't think so any links or any parameters are wrong, or anything is error. There are no error, or there are no mistakes, I believe. So in order to see whether the controls are working proper, let's say that the base link or the link 2, is it rotating? Why it is not rotating? As in, why, what is wrong? Okay, as in, it should have auto-centered, ignore joint limits, drag and drop, URDF file, ignore joint limits. Okay. Uh, it is good, I believe. So so it is moving proper here. Link 3 is also moving proper here, and link 1 it has to rotate. Yep. Link 2 it is proper. Link 4 it is proper. Link 3, sorry, link 4 it is rotating about that axis. It's good. Link 5 is also rotating about that axis, and the gear 1. Mm, Yeah, there is a mistake, right? The gear one, okay, it has to. What we can do here? So since I'm not editing this video, if I get an error, that means even you are going to face that error too. So what I'm keeping those, I'm not cutting here and there in my video section where you know I would be editing the parts where I've made mistake and I will show you the results. No, I would not be doing that. I would directly show you what mistakes I would encounter, because you would encounter the same mistakes and you have to know how to rectify these errors by yourself, right? So let's see, accessory one, okay, kind of rotates like this, but what about gear one? Yeah, we were checking gear one. Oh, it has to multiply, it has to, okay, gear 2 is also reciprocating along with the gear 1, but it has to be in a negative direction. Okay, now I got it. So it has to be in a negative. Uh, so hence we don't have a gear 2 as such. Yeah, it has to go like this once gear 1 is rotating. Hmm. So what we can do is that we go back here and we open tools and we go to the export as URDF. And here in the gripper, the section and everything is proper. We go for preview and export. Over here in the gripper section, which is fixed, and the gate 2, which is mimicking gate 1, gear 1, we could put it as multiplier as -1, right? -1, and -1, -1, and yep. Yeah, and the one thing that I wanted to do is accessory one. Accessory one should even mimic uh, it should mimic gear 2. If I believe accessory, which is accessory 1. This is accessory 1, which has to mimic this gear 2. So let's keep gear 2 and in the same direction as wherever the gear 2 is rotating, and accessory 2 has to mimic the direction of the gear 1, and we go here and so I hope you are understanding what I'm trying to rectify here. I'm just rectifying which is gear 1 and which is mimicking what is mimicking what, right? So that's what I'm trying to do here, and hope everything is fine. Export as URDF. Remember, you have to remove this extension. Oh shit, what did I do? Oh, once again, export as URDF, download. You have to remove this SolidWorks extension, save it. Okay. I hope this should solve a little bit of our problem. Okay, what happened? We'll just run this. We'll put once again this one here and show controls, ignore joint limits. Now let's see what happened to our gear one. Ah, yeah, this is good now, right? This is good. It shouldn't go that far. Mm, Now you might be thinking that how do we set the joint limits? You could go here and set the joint limits. That's up to you. But I would show you one more way where you could set the joint limits even in the URDF file. You don't have to you don't have to do it even in the SolidWorks. But this is good, right? I mean we are getting a control of the gear one as well as the gear two. Once we move the gear one, the gear two is mimicking the joint, mimicking the gear one joint, and it is moving in opposite direction. That's what we wanted, and this is end of this series. I know I've taken a lot of time, but I hope this is understandable, as in how do we convert any uh, SolidWorks to SolidWorks file to URDF file. This is a uh, very small example, as in how did I convert from a CAD model to URDF file, and all thanks to this CAD model is an open source CAD model, which you could get this CAD model from uh, uh, how to mechatronics, I believe. Yep, that's the channel, and you would get the CAD model from there. But if you have understood and if you have seen how did I debug the issue, and if you are building your own CAD model and coming up with the URDF and want to integrate in a ROS2 environment, and I hope and I guess this would act as a base tutorial as in how we could do that. I mean, there are few errors here, as in you could see that we have not set a proper joint limits for each revolute joints. That we would see it in the upcoming class, as in how do we set the joint limits in a URDF file. Until then, hmm, until then, if you have any questions or if you have any doubts, you could post your questions in comment sections, and I would rectify those in the upcoming tutorials. Thank you and have a wonderful day.